In this lesson, we're going to examine a different kind of counting tool, one that's more pattern-based than calculator-based. Okay. One of our big ideas in counting is we want to find these patterns and use the patterns to solve other things. And there are lots and lots of patterns out there. In grade 11, you looked at sequences and series, which are just patterns. There's a really well-known pattern called the Fibonacci series, this one right here, where you take your two previous numbers, add them together, get the next number. So 1 plus 1 is 2, 1 and 2 makes 3, 2 and 3 makes 5, 3 and 5 makes 8, and so on and so on. That's an example of a recursive pattern where you take previous results to get new results. So if I want to find a certain term, let's say I want to find term number 3, I'd have to know term number 2 and term number 1. If I wanted to find term number 10, I would do 9 and 8. And those are all good patterns. One of our big powerful patterns is one called Pascal's triangle. It has a formula made up of terms. And again, it's a recursive pattern where you use previous results to get new results. And the way this pattern works, and you may have seen this before in grade 11, is start off with 1, and then 1 and 1. And then from there on, every other value is the two numbers directly above it added together. So 1 plus 1 makes 2, for instance. And if you think along the edges here, these are always going to be 1s because there's only one number above it, and it's the number 1. So 1 and 1. Okay, 1 plus 2 makes 3, 2 plus 1 makes 3. We could keep adding more rows in. We'll start off with a 1. That's the only number above it. 1 and 3 makes 4, 3 and 3 makes 6, 3 and 1 makes 4, and 1. 1, 5, 10, 10, 5, and 1, and so on and so on and so on. This goes on infinitely. And there are lots of kind of cool little tricks and things to think about in this. And we're going to look at some of those in this lesson. So one of the nice kind of cool patterns is that if you add up the terms in any row of the triangle, it always comes out to 2 to the power of n, where n is your row number. Okay, so I'll go back for just a second. The first row is called row 0. I don't know if you noticed that, but this is row 0, and then row 1, and row 2, and row 3. And if you actually look at the second term, each row, that's your row number. And 1, 2, 3. Row 4 is 4, row 5 is 5. Okay, but if you were to add up the terms in each row, I'm just looking at this, okay, row number 1 adds up to 1. Let's put the triangle over here real quick. Oops, that's not a 3. That's a 1. Okay, row 1 comes out to 1. And if you stop and think about it, 2 to the 0 comes out to 1. Row number 1, which is made up of 1 plus 1, which is 2, is 2 to the 1. Row 1, 2 to the 1. Row 2, 1 plus 2 plus 1 comes out to 4. Or in other words, 2 squared. Row 2, 2 squared. So if I want to find row 3 really fast, 2 to the 3 is 8. Row 4, 2 to the 4 is 16. I can figure out the sum of any row really quick. I can also work backwards. Which row has terms that sum up to 1024? So 2 to the what comes out to 1024. And if I guess and check for just a second, using my calculator, my exponent button, I get 2 to the 10 comes out to 1024. So the 10th row, which starts off 1, 10, dot, dot, dot. I don't know the rest of it, but I know that the terms in that row actually went to 1024. Kind of cool. Now, there are some other things I can figure about rows. If I know some of the terms in the row, I can get a pretty good idea of the rest of it. A couple things I can do. Okay, well, if I go back to the triangle for a second, I don't know if you noticed it, but these rows are symmetrical. Okay, so we're talking about symmetry. The fact that things are symmetrical, let's try to go back to that beginning there. Okay, if we look at each row, the first 3 terms match the last 3 terms. Or the first 4 terms will match the last 4, first 5, last 5, 6 and 6, and so on and so on. So the more terms you know of the row, the more you actually know the entire row because of the idea of symmetry. Okay, we also know we can go forward to get new rows, and we can work backwards to get old rows. Okay, so if we look at this example here, the first 6 terms of this triangle are given. we know it's row 16, right, because my 16 is my second term. Can I find the first 6 terms of the next row or the previous row? Well, of course I can find the next row pretty easily because well, we know you add to get to the next row. Row 17 is going to start with a 1 and then a 17. And any two numbers together will make the next 2 terms. So I add them and I get my next term. Add them up, 23. Get my next term, add them up, 6,188, and get the next term. Now, I don't know the next ones, but if I really wanted to, I could write the last ones out because I know they're going to go in reverse order. 6188, 2380, 680, and so on and so on and so on. Okay, now, that's how I get the next row. I could also find the previous row. I could find the previous row, which is row 15, 1, and then 15. And I can find out terms in that row by knowing that this term and this term have to add to make 120. Or in other words, 120 minus 15 will give me the next term. And 560 minus 105 will give me the next term. And 1820 minus 455 will give me the next term. And 4368 minus will give me the next term. And again, I don't know the middle terms, but if I wanted to, I could write out the last 6 terms, 1365, and so on and so on and so on, because of symmetry. Now, if I think about the 15th row, there's actually 16 terms in it, and I know, from what I've written out, 1, 2, 3, 4, 5, and in reverse, 6, in reverse, 7, 8, 9, 10, 11, 12. I know most of the row. I'm just missing the 4 middle terms by really only knowing the first 6. And Pascal's triangle is kind of handy that way. All right, now we've got some ideas of the triangle. What can I actually use it for? What kind of problems can we solve with it? Well, the nicest problems that we can solve are ones that are called path problems. Path problems are things that have an initial starting point, you know where you start, and they have an ending point. And we have to follow a specific path from one to the next. So for example, the word math. To spell math, I have to go M-A-T-H. So I have to start M, and I have to go then A, then T, then H. Now, I could start circling paths. There's a path, or there's a path, or there's a path. This is going to start getting pretty messy, right? M-A-T-H, there's another path. Yeah, it gets pretty messy. So what I'm going to do instead is, I'm going to think of this as a series of choices. I have to choose the letter M. That has to be my starting point. I then have to choose the letter A. And there's one way I can get to this A. I can go from M to A. Or I could go from M to A. There's one way of doing that way. To get to the T after the M and the A, I could go this way. And there's one way of doing that. I go M, then A, then T. Or I could go to this T over here, M, then A, then T. Or I could get to the middle T by going M-A-T or M-A-T. There's 2 paths. Now, stop for a second. Doesn't that look suspiciously like Pascal's triangle? If I keep that going, M-A-T-H is one way to get to that H. There are 3 ways to get to this H. I could go M-A-T-H or M-A-T-H or M-A-T-H. There are 3 ways. But again, think about Pascal's triangle. It looks suspiciously familiar. 1, 3, 3, 1. So how many different paths can spell math? There's 1 path that'll get to this M-A-T-H. There's 3 for this one. There's 3 for this one, 1 for this one. So when I want to find my total number of paths, okay, we're going to add up each of the finishing points. My total number of paths in this case is 8. There's 8 different ways to spell math by following this array, this triangle of numbers. Yeah, I got one for you guys to try. Can you spell the word McLean's for me? Where do we start? Well, I got to start with the letter M. So I got one way of getting there, and I got one for each of these. To get to the C, I could go MAC or MAC, so I've got two ways. To get to the L's, this is a little bit trickier. There are two ways to get to this L's. I've got MACL or I've got MACL. So we don't have ones along the edge of the triangle anymore. Now I've got a two along the edge. Similarly, I have that two. I've got two for this E and I've got two for this E. Because if there's two ways of getting here, there must be two ways of getting there. In the middle, Pascal's triangle idea, there's four ways. The A's on the corners got to be 2. 2 and 4 make 6. Oh, sorry, I missed. Look at the wrong spot there. 2 and 4 make 6. 2 and 4 make 6. To get to the ends, I could either come from these A's or these A's, which makes a total of 8, 12, and 8. And to get to the S, I can come this way or this way, which makes a total of 20. Similarly over here, a total of 20, which gives me 40 different paths. Remember, add your answers to figure out the overall number of paths. And so we got these kinds of problems where we can spell things, triangular arrays of things. We can take that idea and actually turn into real paths too. A path problem starts at a single point and gets to another point. Well, here I have to walk from point A to point X. And I want to do it directly, which means I don't want to go round and round in circles. If we're allowed to do that, there's going to be an infinite number of paths from X to Y because we just keep going round and round. So I want to go directly from X to Y. Well, to get from X to Y, I have to walk along the streets. There's one way to get to that corner, and there's one way to get to this corner. If I keep walking along this street, there's one way, and one way, and one way. And same thing if I go down here. But to get to the corners in the middle, the interior blocks, I have choices. I could have walked across and down, or down and across. In other words, I have two choices. Well, on the diagonal, does that not look like Pascal's triangle now? Yeah, so if I use that idea of previous paths, add them together to new paths, I can get to this corner three ways. The two from previous and the one from down. This one could be 4, this one could be 5. 1 down and 4 across. If I do the next row, I'll have 3, 6, 10, and 15. Again, we're adding the previous results. 4, 10, 20, 35, 5, 15, 35, and 70. Now, as I go across this next row, I've got 35 from each of the previous. The only number immediately ahead of it is 35, so I have to keep the 35. And similarly, in going down this side, I've got 70s all the way down. But again, those interior blocks I'm going to have to add. So 105, 140, 175, 210. I find it's easier to work across the rows as you're going. Okay, the next one, 175. 315, 315 and 175 makes 490, and this would be 700. Okay, we got 245, 560, 1050, and 1750. And then 315, 875, 1925, that's this one. A total of 3,675 paths. Okay. Again, it's Pascal's triangle, and if you actually look at it, Pascal's triangle totally exists until this point right here. Once you start missing the edges of the triangle, your numbers are changing a little bit, right? You got 5s and 15 and 35 on the edges. Those are part of the triangle, but not the entire triangle anymore. Just like when we did McLean's, we didn't have the entire triangle. Okay, I'm going to give you guys one last try here. We're going to go from X to Y directly. How many different paths do we have? Notice that this time I have some gaps in my thing. So that might cause some issues. We can start with the edges. They're the easiest ones. They're all ones, right? We got 2, we got 3, we got 4. But this one here can only be reached from up here. So there's only one way of getting there. and only 2 ways now of getting to the corner. So the numbers seem to be increasing. Right? We got up to 4, but there was a gap in it. I couldn't jump across it. Think of there being a lake there or a house, so you can't go through it. You have to go around it. It reduces the number of paths. If we try the next one, 3, 6, 10. Well, this one's going to be 11 now because I got my 10 and my 1 and 13. 4, 10, 20, 31, 44. 5, 15, 35, 66, 110, 6. Ooh, I can only get here from that spot, so 6. But I can get to the next one from either of those, so 41, 107, 217. And then my last row, I got 7, 13, 54. I have to go from here and here combined, and that gives me 271. And that's how we can use Pascal's triangle to solve some path problems. So we've got arrays of numbers or letters. We've got path problems. We've got some basic ideas about Pascal's triangle. A couple questions you should try tonight. Make sure you can do these. Number 8 actually has a wrong answer. It should be 69. Give them a try. If you're stuck, come see me.